Now let's go ahead, let's take a little deeper look at these integrals that I have to calculate. Remember, the two integrals I had to worry about was g dl and grad g dot n hat dl. These are the two integrals that I am always thinking about over each segment. Okay. So, we spent an entire module talking about the Green's function and we came up with the 2D Green's function as here, right. So, it is minus j by 4 times the Hankel function, right. So, this one everyone remembers. The one term that we did not calculate so far is what is grad g. Okay. So, just to make the notation a little bit easier, this r minus r prime, it appears everywhere, it is a scalar, it is just a distance, it is a distance between two vectors r and r prime. So, I will just call it rho, okay. And rho I can also write as root of x minus x prime square plus y minus y prime square. Okay. Now, to get at grad g, I need to take the derivative of g with respect to, I can do it in polar coordinates or I can do it in Cartesian coordinates. In this particular case, it turns out that using Cartesian coordinates gives us a simpler answer. Okay. So, here is again piece of information, fact. It is given to you that the derivative of Hankel 2 gives you Hankel 1. Okay. This is sort of given to you, right. There are many properties of Bessel's functions which we will use as we go ahead, and this is one of them. So, now if I want to evaluate grad g, what do I do? I will just use this property, right. So, what is grad g now? So, grad g, using the definition, del g by del x, x hat plus del g by del y, y hat, right, simple. So, we will use this fact over here. So, what happens to the first term? So, del g by del x, okay, and where rho is this term over here. Okay. So, I will write a minus j by 4 will be common. Okay. Then I pop into this, use the property over here. So, dh02 by dx is going to give me a minus k will come, right, because it is a k rho. So, k comes, and then what comes? 2x minus x prime divided by 2 root this thing square plus this thing square, right, along x hat. This is dg by dx, right. dg by dx is just taking the derivative of this term with respect to x, and the second term is going to give me a, again what I get is a minus k 2 y minus y prime divided by 2 rho y hat, right. Chain rule of differentiation, right. I can simplify this, this will become j k by 4 and this one remains over here, right. So, what does this vector look like? So, I have a x minus x hat plus y minus y hat whole thing divided by rho. What is the norm of this vector, length of this vector? It is 1, it is a unit vector, right. And what is the direction of this vector? It is r minus r prime and a unit vector in r minus r prime, right. So, very simply this just becomes j k by 4 h12 k rho, and this is the usual notation, a different script for r, where r is okay. So, this just simplifies the notation, right. So, not I mean we started with g which was h02 and I got grad g is h12, not very complicated, right. Okay. Now, when we are evaluating these two integrals over here, as long as g and grad g dot n hat, as long as these terms are finite, there is no problem. I can use Gauss quadrature rule, numerical integration. The trouble will happen when these quantities begin to, we know that Green's functions have a singularity at the origin. Origin in this case means when r is equal to r prime, that is the singularity. Now, when I am doing this, if we go back to this, when I am doing this integration over here, what am I holding fixed? I am keeping fixed r prime is fixed, right? And where is r going? Over the looping over the entire boundary. R prime is also on the boundary, r prime is looping over the boundary. So, there will be at least one segment where r is going to be equal to r prime, right. So, at those points what will happen? So, this is for example how the Hankel function looks like for very small rho, and this is something you have already seen. So, it has a real part which is well behaved and has an imaginary part that looks like log of rho. And what is the value of log of rho as rho tends to 0? Minus infinity, right. So, this is going to be the problematic integral over here. So, this was for H02. Do you think H12 will be any better behaved? No, H12 also has a singularity sitting at the origin, okay, right. So, both g and grad g, they blow up as rho tends to 0, right. So, therefore, in our integration strategy we have to use two different techniques. So, when r is not equal to r prime, that is the happy case, there is nothing to worry about there. I simply use your numerical quadrature. Right. So, this gamma over here is a constant, it is a Euler constant, some roughly 0.57 or something. Okay. So, where do I get these properties from? I get these properties from the handbook of Bessel functions. So, it is extensively documented, all these special functions have very well documented properties, graphs and all. I will include a reference to it. Okay. Right. So, when r is not equal to r prime, I will use numerical quadrature rules, no problem. Segments where r is equal to r prime, those are what are called singular integrals. These have to be done carefully and we will look at these next, how to evaluate these integrals. Okay. Those of you who have done a course on complex analysis will find some of this familiar. Okay. If not, it does not matter. Okay. So, this is what we will look at, but is the general idea clear? Always keep in mind that our basic motivation is to solve these two equations. In the process of solving these two equations, some terms are easy, some terms are not easy. Okay. Let us take one more step back before we go into more details. Once we have solved these equations, I want to find out finally the field anywhere in space, that is my objective. Then I go back even one more slide, I use Huygens principle to put back these terms which I have evaluated and I can find the field everywhere. So, do not lose sight of the overall picture, right. We are zooming in and more into details, but remember that is what we want to get at. Okay. So, solving the equations and these are the problematic terms. Okay. Now, let us look a little bit more. So, what are the two kinds of singularities that we have? As x becomes very small, H02 I have told you looks like this log of x, okay. And H12 also has an asymptotic form over here, which goes, the problematic term is 1 by x, right. So, as x tends to 0, 1 by x also blows up, right. Now, you can see that both these functions, they tend to infinity in slightly different ways, right. They tend to infinity in slightly different ways. So, let's look at how this manifests mathematically. Okay. So, imagine that I have an integral epsilon to some constant a, okay, and I am integrating log of x dx, okay, and I am going to eventually take the limit epsilon tends to 0. Okay. Now, is this, before we evaluate this, what do you think? I have a singularity at the origin and I am including it in the integration. I am taking the limit epsilon tending to 0. Okay. What do you expect should happen? It should blow up. That's what intuitively you would think. And for this case, what do I have? Limit epsilon tends to 0, same integral. That's the difficult part, 1 by x dx. Okay. If these integrals exist trivially, then there is no problem. I can go back to my original procedure, evaluate the integral over all segments, get my system of equations, and I am done. But before we do that, let us just zoom in and see, is it possible. So, what is the integral of log x? We can do it by parts. You will get x log x minus x, okay, evaluated at epsilon and a, right. If you want to check, just take a derivative, you will get x into 1 by x plus log x minus 1. So, that is log x. Okay. So, this is going to give me a log a minus a, no problem with this because a is some finite number, and then I have to evaluate epsilon log epsilon minus epsilon, right. That is the term I want to evaluate. So, epsilon tending to 0, this guy there is no problem. What about this guy? How do I evaluate this? L'Hopital's rule, right. So, I will do limit epsilon tending to 0. I can write it as log of epsilon by 1 by epsilon. So, now it is in the what form? Well, in this case infinity by infinity form. I can do it in either way, right. So, this will become 1 by epsilon minus 1 by epsilon squared is equal to epsilon tends to 0. So, I integrated a function which had a singularity, and what did I get? I got only this guy. So, a log a minus a. So, this singularity is what is called integrable, right. So, the singularity of G is integrable. So, when I go back into my evaluating those method of movements terms, wherever there was a G term, there is no problem even if the argument rho is tending to 0, because you can see the integral is finite. Even though the function is blowing up, it is like a delta function. Delta function is blowing up, but its integral is finite. So, that is a singularity, but it is an integrable singularity, right. Now, on the other hand over here, I have this second term over here, which is blowing up as 1 by x. Now, when I go to evaluate this, what do I get? Log of x evaluated epsilon and a, okay, is equal to log of a minus log of epsilon. Does this limit exist? This limit does not exist, right. So, this term over here blows up. So, I have a singularity which is going as log x, but it is blowing up at the origin, even its integral does not go. Okay. So, it is like integrating a double delta function. I can integrate it once. I mean, if I integrate it once, I do not get anything finite, but if I integrate it twice. So, when I integrated this once, I got log x. If I integrate this once more, I will get something finite. Integral of log x is finite. So, this singularity over here is in some sense a stronger singularity than log x, right. So, this integral I will call it a convergent integral, and this is a divergent integral. Okay. So, that is what we have to do. So, the singularity of grad G is not integrable, this is integrable. So, we have identified, we have zoomed in and found out that the main problematic character is this H12. Okay. Any questions about this?
What if we approximate this by series, then it will be also integrable?
What if we approximate this by a larger series, right. So, if you approximate it by a larger series, you will get more and more terms, right. So, you will higher powers of x you will get, but the point is that you cannot ignore the first term. The first term will always be there, right. So, each of those terms should converge to a finite number, and that will not happen, right. So, if the first term itself does not converge, there is no point going further, it is not going to converge. Yes. So, the question is that if I integrate this H12 using a quadrature rule, will I have the same problem? Answer is yes, because what you are trying to do is in some sense, you have some integral like this, and you will take the value of the function at some finite number of points. If you use the quadrature rule, you will get some answer, because it's numbers. You will put, what is the quadrature rule saying? Summation wk f of xk. As long as you chose xk to be not 0, right, you chose it to be some finite number, you will get some answer to this, but theoretically this integral is divergent. So that's actually even scarier, because you will get some answer for it and you think it exists, but underneath the hood it does not exist. There is a special technique of modifying quadrature rules when you know that there is a singularity inside it. It's called singularity extraction. Okay, but as it is, if you use a quadrature rule, you will get a misleading answer, because theoretically you can see that this integral is divergent. You should not, if you get an answer, you should know that you should be suspicious.